Today I will be talking to you about augmented language models and how to get models to use tools. So before I dive into this topic more deeply, I first want to motivate why we would actually want models to use tools. And to do so, I want to show you a couple of responses that I get when I currently use ChatGPT. So my first query is, who is the current president of the United States? It says, I don't have real-time data or internet access, and my knowledge was last updated in September 2021. Not super great, right? In my second query, I've asked, what is the result of this computation? And it says this following result. But unfortunately, it's about like 300-ish off of the real answer. And then finally, I've asked, what day of the week is it today? Pretty basic question, but it says, I don't have the capability to access current time or date information. So this is pretty disappointing. And what all of these queries have in common is that they could have really benefited from the use of external resources. And what I mean by that is, in the first case, we could have really benefited from the usage of a QA system that does have access to current information. In the second case, we could have really benefited from a calculator tool because that's exactly what a calculator can do. It can perform this computation perfectly. And finally, we could have really benefited from a calendar tool because the calendar can definitely tell you what day of the week it is today. And so even with the most powerful models that we have today, we still have limitations like not having up-to-date information or the propensity to hallucinate. And this can likely be remedied by external tool usage. And what exactly is a tool? Well, I'm taking the definition of a tool to be a pretty broad one. It's basically any kind of black box interface that takes in an input and gives you an output. So for instance, the QA system, you give it a question, it gives you an answer, and so forth. So we also saw in the previous slide that we have a calculator tool, a calendar tool. We can also imagine a search engine as being a tool. And we can even imagine another model as a tool. And you might want to call another model because this other model is maybe more powerful or maybe more specialized at a particular task. So with this definition of a tool in mind, this is what the roadmap of my talk is going to consist of. It has three major parts. The first part will talk about manual tool usage. And this is tool usage that is basically always prompted or triggered by the system or the user. And in the second part, we'll turn towards getting the model to learn for itself when to use a tool, learning to know which tool to use if there's a set of tools, and then also how to use that tool properly. And then thirdly, we'll look at some challenges and future applications where tool usage might be really handy. And a lot of what I'm going to talk about is actually also discussed in this survey paper, Augmented Language Models. It appeared in TMLR earlier this year. And the QR code is linked up here in case you're interested in a more comprehensive overview. It basically talks about how to reason about tool usage, how to use those tools effectively, and maybe even act upon the external world using those tools. Okay, so now for the first part, which is manual tool usage. And again, this is tool usage that is prompted or triggered by the system, meaning the model doesn't have autonomy in deciding when to use that tool or how. And a classic example of this is actually retrieval-augmented language models. So in this setting, let's say you have a query, what is the ratio of children to dogs in San Francisco? And what you'll do with this query is you'll send it to the retrieval engine. The retrieval engine will return you a set of references. And then you'll use those references in tandem with the query in order to produce a generation. And in this case, surprisingly or not, 2016, there were more dogs than children in San Francisco. And so this is a setting of manual tool usage because you're always going to do that retrieval for every single query. There's no choice in the matter. And you're always going to use those references that you get back from the retrieval system no matter what. So you always do this, and this is why I refer to this as manual tool usage. And sometimes this makes sense. So for example, let's see this task here. It's called Improving Citations in Wikipedia. This is actually work that appeared in Nature Machine Intelligence about maybe a week ago, 2 weeks ago. And basically the idea is for every claim in Wikipedia, we want to provide a citation for that claim to make sure that it's verifiable and it's legit. So here we have this claim about the Blackfoot Confederacy. What we're going to do is we're going to retrieve from the retrieval engine, get a set of references, and then we're going to send those references and that claim to the verification engine, which will pick the best reference that best supports the claim. So this is obviously a case where you would want to do retrieval for every query because that's kind of the whole point. You want to pick a reference that best supports the claim. And but sometimes you won't always need to necessarily do retrieval. So for example, here I'm showing you two data sets, natural questions and trivia QA. And these are question answering data sets. The last one in the last column is called Fever, and it's a fact-checking data set. And you could argue that maybe you don't need to do retrieval for these data sets because with larger and larger models that we're seeing these days, you can store more information in the model itself, and you don't really need to outsource to a retrieval system. And what I'm showing you in the 4 rows is 4 non-augmented language models: Chinchilla, GPT-3, Gopher, and Palm. And in the last row here, we have Atlas. And Atlas is basically Atlas is basically a pre-trained retrieval-augmented language model that is designed to learn knowledge-intensive tasks from just a few training data points. And even though Atlas is so small, it's only 11 billion parameters in size, it's able to outperform the other non-retrieval-augmented language models pretty substantially. And even though it's about 10 to 50 times smaller, we see that we do get this benefit from being able to retrieve and be able to leverage that external tool. Okay, so I showed you examples of retrieval-augmented models, but you can also think of other models or another model as an external tool. And a good example of that is this model, Shepherd. Shepherd is a critic for language model generation, and it's designed and fine-tuned to give feedback to an assistant's responses. So let's say I have this query, and my assistant responds with some response. But the response could be improved. It could be made better. And that's exactly what Shepherd does. It gives you feedback on what was lacking in the original response and how you can make it better. So this is a good case where you can use the original response, you can use the feedback from Shepherd, and you can get the assistant to improve upon its original response. And this is a good case where we can think of another model as an external tool. And it's not just another model or a different model that we can think of. We can also think of the model itself. Maybe you want to call the model itself, again, as an external tool. So for example, I have this model, Peer, a collaborative language model, which appeared in iClear this year. And Peer is a collaborative language model that is designed to work with you, the user, on building whole articles from scratch. So let's say you want to write a Wikipedia article about somebody. And it has 3 major modes. It has a planning mode, it has an editing mode, and it has an explanation mode to explain the kind of edit that it created. And then it repeats this process so that it can iteratively build upon the article that you want to create. And now this is where Peer may call itself. When the user doesn't actually input a plan, it will call itself to create that plan. So let's see an example of what Peer can do. Here I'm going to create a new page about Peer. So Peer is a language model, as I just mentioned. Now we're going to add info on what the model can do. It can write drafts and provide explanations and so forth. We're going to add a citation for the model, and it pulls a citation from arXiv, which is the paper itself. And then we're going to add the 4 steps that I mentioned, which is to plan, edit, explain, and repeat. And now we're going to mislead the model and ask it to add info on the scandal. And there's not actually a scandal, but it's followed your instructions because that's what it's supposed to do. It's supposed to be a helpful model. It's added a sentence. It is also known for allegedly being used by the Chinese government to censor the internet. That's not super great, and now we've derailed our editing process with this weird sentence, and maybe we don't know what to do, so we can let Peer decide what to do next. And when you let Peer decide what to do next by clicking that blue button at the top, it decides to do the right thing and remove the unsourced claim that you introduced previously. So this is to show you an example of where you might want to consider the model itself as an external tool. Okay, so I showed you examples of retrieval-augmented models, model-augmented models, where the tool usage was always clear when to do and how. But now we want to get towards work that actually gets us to teaching the model to know when to use the tool and how. So the first of this work that I want to discuss is called active retrieval-augmented generation. And it starts out pretty simple, similarly to the retrieval-augmented setting that I just discussed. Let's say we want to generate a summary about Joe Biden. We're first going to give this claim to a retrieval engine. And this retrieval engine will give you references A, B, and C. Then we're going to generate the sentence, Joe Biden attended the University of Pennsylvania, where he earned a law degree. Now, what we're going to do differently in this setting is we're going to identify if there's any low probability tokens in this sentence that it just generated. And in fact, there are. The model is not very confident about generating Pennsylvania. It's not really sure that he went to Pennsylvania. So what we're going to do differently now is we're going to help the model out by doing a second retrieval. And when we do the second retrieval, we actually use the generated text that the model spit out. So we're going to use Joe Biden attended the University of Pennsylvania where he earned a law degree. But we're going to mask out the Pennsylvania part because that was a low confidence token. And the reason we mask that out when we do retrieval is because in the event that Pennsylvania is not correct, we don't want to go snooping around for references that reinforce that misinformation. We want to look for more information about where he actually went to the university. And so we do the retrieval with that generated text, with the masked out low probability stuff, and we get references A prime, B prime, and C prime. Now let's try generating again. When we do the second generation, it's actually found evidence that he went to Delaware, not Pennsylvania. And so it regenerates with Joe Biden attended the University of Delaware. And this, in fact, is true. He went to Delaware and not Pennsylvania. So this is an example of the model knowing when to use a tool because we did this second retrieval only in the case where it had low probability tokens. If there was no low probability tokens, we would not have done the second retrieval. So this is a good example of where we use the model's internal understanding of what it generated and what it suspects went wrong in order to decide whether or not to do that second or external tool usage call. Okay. But it's not just, we don't just want the model to know when to use the tool. We also want it to know which tool to use. Let's say I give it like 5 tools. We want it to know which tool to pick and also how to use those tools if it is given a set of tools. And so now I'm going to talk about this work, Tool Former, which is a work that's going to appear in NeurIPS as an oral presentation. And the way Tool Former works is it indicates to you that it wants to use a tool through natural language. So for example, if I have this query, the result of blah, blah, blah is blank, it'll tell you that it wants to use the calculator tool by putting in square brackets calculator, and then in parentheses, it has the input parameters. So this is really nice because we can operate as we've always done. We can use natural language, and we can just take this API call or tool call that the model is indicating, and we can parse the string in order to get the in parameters and call that external tool. And at this point, you may be wondering, well, how does this relate to ChatGPT plugins or all the other previous work that may be surrounding tool usage? And we're definitely not the first one to do this type of work. And I don't work for OpenAI, so I can't tell you specifically how ChatGPT plugins work. But what I can tell you is that most of the prior work that came before this paper followed 2 kind of major lines of work. And the first is human annotation, where you get human annotators a bunch of queries, and you ask them what types of tools might be helpful here, and how might you actually use those tools. So they'll manually annotate those. And this is obviously going to be expensive, both in time, money, resources, etc. It's not going to scale well if you have a lot of tools, a lot of queries. And secondly, another major line of work is through prompting. So prompting basically assumes that the model is fundamentally capable of understanding how to use tools, but you just need to give it a good explanation of the tool and also a couple of examples. And this has some major fallbacks, like being too specific to the specific tool. So maybe you make it for one tool, but it doesn't generalize well for another tool. You'll have to redo this process every time you get a new tool. And as we also see in this paper, Active Learning Principles for In-Context Learning, the model is super sensitive to what kinds of examples you pick, and so your performance is going to vary wildly. And as we see in this paper, we will leverage prompting, but we'll see that the model makes a lot of mistakes when you rely just on prompting. So the way that Toolformer differs is that it's a fine-tuned model. It's fine-tuned to know how to do these tool usage calls. And the way that it's fine-tuned is we first create a new training data set augmented with these API calls in natural language. And then the second step is obviously to fine-tune our base model, GPT-J, on that new data set. So GPT-J is a 6 billion parameter model. It's nowhere near the size of like GPT-3, but it's still capable of using tools, as I'll show you in just a second. And so what kind of tools does Toolformer use? Well, we use 5 different kinds of tools. We wanted to pick tools that were kind of different but simple enough and a little bit diverse. The first is that QA system I've been talking about. The second is a Wikipedia search tool, so it searches Wikipedia. The third is the calculator tool. The fourth is a calendar tool, and this calendar tool basically doesn't take in any input parameters. It just will always tell you today's current day and the date. And then lastly, we have a translator tool, which will take in text and then give it back to you in English. And so now we move on to the first challenge of how do we create this data set that's augmented with API calls? And the way we're going to do that is by taking a standard language modeling data set and then augment it with API calls that are actually useful. So here we might have a sentence, Pittsburgh is also known as the Steel City. And an ideal API call that we might want to put in here is what other name is Pittsburgh known by, because that would return the Steel City, which is useful for completing the text, which is the Steel City. And the data set that we use here is called CCNet. It's basically a lot of text from the web and so forth. And the data set that we get at the end of this process has those useful API calls. We're going to refer to that as CCNet API. And now you may be wondering, well, why are we using this standard language modeling data set? Can we use any data set? Well, we decided to start off with this language modeling data set because even though we want to imbue the model with this capability of using tools and knowing how to use tools, we don't want to disrupt any of the core language modeling capabilities that it may already have. And in using a data set that it's been pre-trained on, or it's seen before, or something similar to what it's seen before, we can minimize this risk as much as possible. Okay, so now the question is, how do we get from CCNet to CCNet API? And the way we do that is through 3 pretty simple steps. The first step is to generate API calls through prompting. The second step is to execute those API calls. And finally, we're going to filter out API calls for the ones that aren't actually useful for anticipating the rest of the text. So turning to the first step, generating API calls, what we're going to do is we're going to prompt the model. And we prompt the model with this following prompt. Your task is to add calls to a question answering API to a piece of text. The question should help you get information required to complete the text. You can call the API by writing QA question, where question is the question you want to ask. Here are some examples of API calls. And the example input I've shown to the model is Joe Biden was born in Scranton, Pennsylvania. And the example output that I've shown to the model is Joe Biden was born in, with a QA call to which says, where was Joe Biden born? Because this would help in anticipating Scranton, followed by a call in which state is Scranton, because this would likely help in anticipating Pennsylvania. So these are some ideal examples I'm showing the model, and it's followed by the actual input I want the model to try. And I'm only showing you one example here, but we usually show it 3 to 5 examples based on how many will fit into that context window. And I'm only showing you the prompt for the QA system, but you can also imagine that we do the same thing for all the other 4 tools. Okay, so now let's take a look at a couple of the generated API calls that was produced here. Here my input is Pittsburgh is also known as the Steel City. The first one that it generates is in which state is Pittsburgh. The second is what other name is Pittsburgh known by. And the third is what is the second city in Pennsylvania. The first one, in which state is Pittsburgh, doesn't seem that useful. We're not really looking for Pennsylvania here. The second one seems really promising, as we've seen before. And the third one doesn't make a whole lot of sense because obviously there are more cities than just 2 in Pennsylvania. So really what you can see here is that we get a mixture of useful API calls, but also good API calls that aren't useful, or some API calls that are just nonsensical. And now we move on to the second step of executing those API calls. So in this case, we're going to take that natural language API call, we're going to parse it, we're going to get that input string, we're going to give it to the question answering system, and we're going to get those respective answers. So in this case, that would be Pennsylvania, the Steel City, and Pittsburgh. And then we're going to embed the answer back into the natural language text, and we're going to do that by indicating a right arrow followed by the answer, which is Pennsylvania. And at this point, this is also the point where we would filter out any generated API calls that don't actually return an answer, or maybe they throw an error with the tool, or they're not syntactically correct in some other way. Okay, and now we turn to the most important bit, which is to filter out those API calls. We want to make sure that this data set is of high quality, and we want to make sure that these API calls aren't just distracting or useless. We want to make sure that they're useful for completing the text. And the way we do so is through model-based perplexity. And model-based perplexity is basically a measure of how confident the model is about the rest of the text. So let's define this L function here, which is the negative log probability of the rest of the text given the prefix of the text. So let me show you an example. Under the no API call setting, your prefix would be Pittsburgh is also known as. And the perplexity here would be 2.5. And the thing to know about perplexity is that when it's lower, it's a good thing. So this is basically because you would want the model to be least perplexed about what it's about to see. And so in this case, we have 2.5. In setting B, we have the non-executed API call. So the prefix would be the same as before, but now we're going to add this QA call, what other name is Pittsburgh known by. And we're not going to put in the answer to that because this is the non-executed API call setting. And the perplexity here would be 2.1. Then thirdly, we're going to execute the API call. And so the prefix here would be the same as in B, but we're actually going to put the final answer there. And now the perplexity is 0.8. So the intuition here is we want the API call to be useful, and in addition to that, we also want the answer to the API call to be really useful. So we want the difference between C and A and B to be as large as possible. We want the perplexity to reduce as much as possible. So this is why we define usefulness as the minimum of setting A and B minus the perplexity under setting C. And in this case, we get a positive perplexity of 1.3. So likely this would be a useful API call. And oops, now we're going to okay, so here are some examples of usefulness and the respective texts. I'm showing you the example from the calendar tool. The WL will be open on Friday. And then the calendar tool is telling us that Thursday is March 9th. So we can kind of infer from this that the Friday is going to be March 10th. And so this is a useful API call, and it does get a high score of 2.11. On the other hand, we have this example from the calculator tool. The model has seen 85 patients, 23%. It does the reasonable thing and thinks maybe the person will want the ratio, and so it divides those two numbers. But this ratio is actually not what the second sentence needed, and so it gets a low usefulness score, even though it was a reasonable guess. And now what I'm showing you is the number of examples that are left over after we filter out all the non-useful examples. So there are two thresholds that I'm showing you here. In the light blue, we have a threshold of 0.5. And in the dark blue, we have a usefulness threshold of 1.0. And obviously, you can see that when you use a threshold of 1.0, you get a lot less examples left over because it's a more stringent criteria. And you can also see that for the Wikipedia search, we get a lot more examples left over than, say, for the calculator and machine translation tool. And it's likely because, if you're taking text from the web, there's not a whole lot of opportunity to use a translator or a calculator, particularly in this data set, CCNet. So now we're going to take all the examples that we have left over that are useful API calls. We're going to combine them from the 5 tools. We're going to cap the number of examples per tool at 50,000. And this is the data set that I refer to as CCNet API. And now with this dataset CCNet API that has these augmented API calls, what we're going to do is we're going to go back, we're going to take that base model GPTJ, and we're going to further fine-tune it on our new data set. And this is the model that I refer to as Toolformer. And now comes the task of actually evaluating Toolformer, if it's good at using these tools, if the performance of Toolformer is better than other models. And we're going to do so by looking at 5 different kinds of tasks. Each of these tasks was chosen to ideally test one of these tools. So we look at fact completion and question answering. These are very factual questions. Hopefully they use Wikipedia search or the QA system. We also have mathematical computations. Hopefully this uses the calculator tool. And we also have multilingual questions where the context is given in English, but the query is multilingual. So you need to understand the question in order to provide the right answer. And then finally, we'll look at temporal questions, which need some awareness of what point in time it is. And this is designed to target the calendar tool. And here are some results from the factual and mathematical tasks. We can see that Toolformer is doing really well in the case of fact completion and math. So it's not only beating the base model GPTJ, it's also beating GPT-3 substantially, which is, to remind you, GPT-3 is 175 billion parameters. Toolformer is only 6 billion parameters, and it's able to greatly improve upon the performance of this model that's about 30 times larger than itself. In the third task of question answering, we disabled the QA system actually for this evaluation because a lot of the examples in the QA system that the QA system has seen are also in this benchmark, so we thought it might be too cheating if we allow that system to still operate. So we're not beating GPT-3 in this case, but we are still improving upon the base model, which is GPTJ. And now turning to the temporal and multilingual tasks. The first data set I have here is called the DateSet dataset. It's a data set that we designed, and it has questions like, how many weeks is it until Christmas? Or what day of the week was it 15 days ago? So this needs information about what specific day it is today. And as you can see here, GPTJ and GPT-3 are really suffering here. They don't know what day it is today, and they're probably just guessing, and so they get non-zero performance, but it's still pretty bad. Whereas Toolformer is able to know what day it is today, and so it's able to improve upon this substantially. Now for Temp Llama, we have questions like, who is the quarterback of such and such team? Sometimes they're very specific questions, so this is a very challenging data set to begin with, but it requires temporal knowledge because depending on what point in time you ask this question, the answer to the question may change, just like the President of the United States, for example. And Toolformer and GPT-3 are pretty much on par with each other. They do slightly better than the base model, but we think that Toolformer is not getting a lot of benefit here because you actually need 2 tools for this data set. You need to call the calendar tool to get the point in time that it is, and then using that date, you can call the QA system or the Wikipedia search and ask who is the quarterback for this particular year. And the way that Toolformer is designed, as I show you, we do the tool usage calls individually for each tool. So basically only one tool can be used per example. And this is really limiting and probably why we don't see this additional benefit here. And finally, for the translation task, we see that Toolformer and GPTJ are basically on par with each other. We have a suspicion here that GPTJ, because it's already seen multilingual text, it has an idea of what the question is saying anyway, and so it doesn't need to leverage the translation tool. So you're not really going to see a whole lot of benefit here. So we've seen cases where tool usage, particular tools, are really helpful, and maybe for some others, they're not as helpful. But now let's turn to a different question, which is the fundamental question of, is there a minimum size of a model that we need in order to be able to get models to use tools? Because when models are too small, they often can't reason very well and possibly cannot use those tools. So here what I'm showing you is a graph of performance along the y-axis. And then along the x-axis, we have the size of the model in terms of number of parameters. And we're going to look at three different models. The first is GPT-3, which is that 175 billion parameter model. It doesn't vary according to size, so we're just showing it for reference. Then we have that blue curve, which is Toolformer. It's the model that's able to use tools. And then we have this red curve, which I'm calling Toolformer disabled, because we're going to disable tool calling here, meaning we're not going to allow it to leverage external tools. And we're going to disable this by doing constraint decoding. So anytime it tries to attempt that square bracket, we're going to say, no, try something else. And so what you can see here is that for the fact completion benchmarks, for the smallest two sizes, you don't see a difference between the tool using Toolformer and the disabled Toolformer, which means that the model isn't smart enough yet to know how to leverage those tools to the best of its ability. And once you get to the third largest size, you do see this performance emerge, meaning it is able to take advantage of those tools. And then this gap in performance is sustained for the rest of the sizes. We see the exact same thing for the math benchmarks. And we also see a very similar thing for the QA benchmarks. Even with the smallest size, you see this small performance difference, and this performance gap is sustained through the rest of the model's sizes as well. And now I want to revisit the original question of whether or not Toolformer is still a good language model. So what I mean by that is we used CCNet because we didn't want to disrupt any of the core language modeling capabilities that the model may have. So now is a good time to revisit that question. Did we actually do any harm here? And the way I'm going to evaluate that is by evaluating perplexity. And if you can recall, perplexity is better when it's lower. We're going to look at two data sets, Wikitext and CCNet, and we're going to look at three models, in particular GPTJ, which is that base model with no fine-tuning, GPTJ plus CC, which is basically GPTJ, but it's further fine-tuned on CCNet. CCNet is the one that doesn't have API calls. And we're also going to evaluate using Toolformer disabled. And I'm using Toolformer disabled for this analysis because the way that you compute perplexity, there's no really good analogous way of doing so when you have all these API calls. So suffice it to say, we're going to use Toolformer disabled, which is still the same model. We're just going to prevent tool usage. And when we look at the perplexity for Wikitext, we see that the perplexity is pretty much on par. We do get this additional increase in perplexity when we do fine-tuning, but it's not really because we did this API call augmentation. And we think that there is this increase in perplexity maybe because the pre-training data for GPTJ, which is called the pile, is maybe more similar to Wikitext than it is to CCNet. But when we look at CCNet, we see that the perplexity is almost basically the same. So we feel pretty confident that this API calling, even though it may look unnatural, it didn't actually disrupt any of the core language modeling capabilities that GPTJ had. Okay, so now I want to revisit where we are in this outline. I told you about manual tool usage, which is tool usage that is always prompted and always triggered and by the system or the user. We saw retrieval-augmented models. We saw user-augmented models, model-augmented models. And then we turned towards getting the model to learn how to use tools themselves and also which tool to use and how. We saw this first with retrieval-augmented generation, where it learned when to do that second retrieval. And then we saw this with tool former, which knows how to do all three of those components by itself. And now we're going to turn to future challenges and applications where tool usage might be very interesting and useful. So the first, in particular, with regards to tool former, we want to experiment with more powerful models, in particular Llama, which Meta came out with this year. It still remains an open question of whether or not powerful models rely more or less on tool usage. Maybe they have more complex cases of how they use tools. Maybe they rely less on tool usage. This definitely remains to be explored. We also want to look at interactive or chained hierarchical tool usage. So as you can recall, tool former only does one tool per example, and we can really unlock a lot of new applications if we do this chained, interactive, and hierarchical tool usage here. We also want to look at more advanced tools like a Python interpreter or database access. So code generation, for example, like GitHub Copilot might be a good example of this. There's also the question of whether or not we can get active tools to work. So an active tool is basically a tool that changes the state of the world. Right now we just have passive tools that only return a result. But maybe you want to change the world by booking a flight, sending an email, reserving a restaurant reservation, and things like that. And then lastly, we also want to be able to easily adapt to new unseen tools. So let's imagine the case where you have thousands of tools. How are you going to navigate that space of tools? How are you going to readily adapt to a new tool on the fly? Which can be important in certain cases that are very time sensitive. And this is definitely a significant challenge that remains. And now the question is, what types of applications might benefit from tool usage? And one major application that I could think of is multi-source retrieval, in particular personalization. Personalization, in particular personalized AI agents, have been talked a lot about this year. Let's say you want your AI agent to help you, plan your day, plan a vacation, achieve your wellness goals. These are maybe all use cases that you may desire as from your chatbot. And let's say we have the simple question of, when was the last time I went to Tokyo with my sister? This may conceivably need information from your Google Maps, maybe your Facebook, maybe your photos. And we can conceive of a world in the future where your AI agent has access to all of these things, right? It has access to Spotify, Netflix, your Apple devices, your watch, whatever, given your permission, of course. And we can think of these as tools. And as we show in Timeline QA, a benchmark for question answering over timelines, which appeared in ACL this year, language models today are really, really bad at doing this temporal reasoning and being able to source from all of these multi-source sources. And so this is definitely a challenge that remains for personalization. There are also different kinds of problems when it comes to multi-source retrieval. You can have the case where you have different properties of the same entities. So let's say we have two tools. One of them gives the menus of the restaurant, but the other one gives the reviews of the restaurant. You can also have the other case where they're different entities, but they have the same properties. So maybe one is American restaurants, the other is French restaurants. And you can also have the case where one is a superset or subset of the other, or maybe one is more authoritative or more preferable. But you won't necessarily know this a priori. You will need to learn this very quickly. And so this is also challenges that were discovered in the field of data integration many years ago and are further outlined in this paper, Learnings from Data Integration for Augmented Language Models. Another great example of multi-source retrieval is actually recommendation systems. So if you imagine the recommender system that we have on Facebook, this recommendation system has a ton of features and signals to leverage from. It has these feelings, it has activities, it has reactions. You have this hide post thing, report post, unfollow, snooze, unfriend, block, friend, comments, messages. Like there's so many you can't even imagine. And being able to judiciously decide which resources and features and signals to leverage is going to be important here because you don't want to distract the model. And it's also going to be more efficient for you, right? Because you're going to have to process less information. So just look at these two posts, for example. the left post says, Heathrow Airport asks airlines to stop selling summer tickets. It's probably going to need, current world affairs, if any kind of tool, in order to understand this content. But the post on the right says border collie working from home. This is going to be a different kind of post, right? It needs information about COVID. It needs information, maybe from an emotion classifier. Maybe you want to look at the comments. Maybe you want to look at the reactions. Maybe the friend network. In any case, you can see that there's going to be very different kinds of content that are going to need very different kinds of things. So being able to prudently use what's available to you is going to be a significant challenge here. And also a place where external tool usage can come in. Another great example of where we can use tools is multi-hop reasoning. So for example, if I tell you, what is the height of this building? You first need to figure out what exactly is this building, and you may need to ask a image recognition system what this building is. And then you can ask the search engine, hey, what is the height of the Big Ben? But a lesser explored place for multi-hop reasoning is actually situational social reasoning. And this is particularly challenging because some things that may be okay in certain situations can be completely not okay if you change something very small about the situation. So let's take this very simple example. You're drinking hot coffee. This is totally okay if you're in a cafe and you're the customer. But if you're the barista working on the job actually making the coffee, it's probably not okay for you to be drinking at the same time. But now if I change it to a barista who's taking a break, then it suddenly becomes okay that I'm drinking that hot coffee again. And what we see in this work, Norm Bank, a knowledge bank of situational social norms, models are really, really bad at doing this non-monotonic reasoning, even though humans are super good at it, because we have this experience of what's okay in situations and what's not. And very similarly, we see that moral and social reasoning are particularly challenging. So for example, in this work, the moral integrity corpus, we probe language models with a lot of questions that require making a moral judgment about things. So in this case, I've asked, would it be better if gay marriage was legal? And the model says, I don't think it would be a good idea. Bisexual people are more likely to cheat on their partners. And maybe the model would have come to a much better conclusion if it had more information from the internet, or maybe more information about how other countries that it's legal in, how it's worked out for those countries, or maybe a distribution of popular opinion in the world. But in any case, it's going to need understanding of a lot of different things, maybe even like ConceptNet, for example. And what we do in this work is we build these rules of thumbs to try to help guide the model to make a good moral judgment. But even in this case, we still see that the model struggles in certain situations because it does have that limited understanding about the world. Okay, so now you might ask, what are some actual specific applications where we might want to use tool usage? And what better way to come up with this list than by asking ChatGPT again? It provides me this list of things like information retrieval, travel planning, knowledge management, scientific research. All of these might be really interesting and cool, but they kind of all follow under the categories that I outlined earlier. They're either multi-source, they're multi-retrieval, they require being judicious about which features you use. But I think a major challenge at the heart of this is not only being able to access these tools, but being able to take a query, decompose it into subproblems, identify which tools are going to help you do those subproblems, and then put the results back together, execute that plan, and come to a reasonable conclusion. So being able to plan and decide how to figure out the solution is going to be the key here. Okay, so thank you for coming to my talk. I really enjoyed giving it. I'm so fortunate to be invited here. These are all my collaborators that I've also been very fortunate to work with. A lot of them are from Meta, some of them are from Stanford. I'm sure they would be super happy to answer your questions about their relevant work. You can also message me at janeu@meta.com. And here is a list of all the works that I cited throughout the talk. So happy to take any of your questions now or later or whenever.